I can see. I agree. This is much more crocodiles than the previous month.
And there are a horse.
A horse?
Dog. It's a dog, yeah.
A dog? Or maybe a mouse?
This was kind of easy.
Easy?
So we need to make 3 knots.
Do it.
Are we waiting until Butty will come?
Well, he says that he will come maybe a little bit late. I don't know. Should we wait?
Well,
we
the
just
presenter is busy. The talk is ready. We are just waiting for more people to come.
The talk is ready.
How to make this knot with that?
What?
How to make this knot?
You just twist.
Yeah, but it's...
And then you hold it, and then you twist.
You need to hold it center.
I think it might be easier if you did a one way,
You know,
then the other way, then the other way. So like this. Then you bring,
Oh, we need to make 3 knots and...
and then you can twist them here, like that. Then another 1, 2, and then 3. Then these come in like this. Oh, whoops.
Yeah, I got it.
Like that.
So this is the tail.
And then you do the bottom one. Like that.
There
Oh
you
wait,
go.
no, I need to turn this one. My wiener dog
Looks
there.
like a dog. And what is yours?
would follow
And
me.
yours is horse.
My dog is different breed. So yeah.
Water.
What? What?
Oxygen, hydrogen.
Players?
Yeah, this good. It has to have 2, I guess. Long pairs.
So you're halfway to water.
Oh, it may be.
See, my dog is like long neck dog.
Yeah, mine's a wiener dog.
Which called giraffe.
Your dog has his head backwards.
Whatever, there's something dog. Oh yeah, it just look like dog now.
Yeah, because the head was back.
Wow.
I think his looks.
And you said you are not a clown.
I just followed pictures.
Now you need to play. Take another.
Hi, how are you? Let's become friends. You know, like there's an anecdote. Can you play oh. Can you play chess? Do you know how to play chess? Yes, of course. And like imagines that you have a figures. Hello, horse. Hello, a king.
So, you ready to start? Or you'll wait until Bacteria pops up?
I think it would be most suitable for bacteria to not just come in at the middle, but if we want to start, we can.
But he promised to show up.
He says that he will come, but I didn't realize where he was placing at that moment. How long it takes him to come? Maybe if he's in research,
That's like 15 minutes.
drive and
Or driving is still 15 minutes.
then parking,
Yes.
and then coming.
No, now you can click here across the road.
Yes, but I don't know if he.
Huh? That's all I ever wanted.
Yeah. I'm just waiting for it to pop.
Just randomly and make something. There's a lot of
have a dinosaur there. It's a green one.
Yeah, I think it's virtually the same thing as a dog.
With less features.
That's a miniature dinosaur. What is that? I don't know.
It's a pretzel. Movie strip.
What is it? Ah,
We are populating the room with dogs.
so this is kind of a strange dog. It's pretty symmetric dog. Doesn't matter how you take it. This is a dog.
It's an
and this is a
isomer
dog.
of a dog.
This is also a dog looking backward.
Actually, I think
That's the next step of evolution. Yeah.
I think this makes the best dog.
You cruel pie.
No, because
You just squeeze the dog.
the ears were as big as the legs.
Here is a sausage.
Sculpture of sausage.
Oh.
I suggest to start.
Okay, we can begin.
Accepted.
So today we're going to talk about DFT and organometallic complexes. Does this work? Or? Yes. So Dr. Soon sent a whole list of things to bacteria and myself that's related
how
to
many
this.
of them?
I don't remember. I think it was like 70. I think it starts in like 2009 and goes to now. It's not-
2009 is a year, is not number of papers.
Yes.
Yes, yes. So the basic outline, we're going to talk about the framework to describe the organometallic complexes. Wherever you see OMC, organometallic complexes. So first, like we're going to talk about DFT, then predicting the energy, other methods, and then stuff on spin-orbit coupling. So let's get into DFT. So I'm kind of focusing on this presentation on iridium because depending on which metal is in the center would dictate which functionals are best, and I have the most experience with iridium. So PBE looks very similar to experiment. It's not bang on, but it's very good. The general trend is that the absorption has about the correct energy, but the emission is redshifted or lower in energy. B3 lead has very similar character as PBE 0. And depending on your structure, one works a little bit better than the other, but they are very similar. Can B3 lead sometimes works. I think Jabed, you had some that you had can B3 lead work better than PBE and B3 lead, right?
That's having the excited state, not in the ground state.
So the excited state was correct qualitative and quantitative, or was it just qualitative?
Quantitative transients.
Yeah, so, and that's where I said they are blue shifted, and then I've used omega B97XD once because it has a dispersion correction in it. That's what the D is, and this was when we had a dinuclei, so two metals, and this was needed because the wave function kind of was degenerate on the two metal centers, so you needed to have a more diverse, more spread out functional than PBE or B3 lead.
What's the
And
difference between that?
difference between which?
Between all this.
So this is a hybrid functional. I believe this is,
Another hybrid function.
yes, this is a long range corrected hybrid functional.
And another.
Yes.
Long-range, but how are they different?
So
Why is the name different?
the correlation, the exchange portion and the percentage of Hadji-Fock is different. So I know PBE0 has 25% Hadji-Fock, and then the rest is a functional, came up with Peter Burke, and I forget the other people's names.
This is only difference?
To be honest,
Then why not just to use it like some abbreviation in front and then just put this percentage or whatever, 25, 30?
Correlation
Why they
also
all have,
different, yes.
why they all have all these different names?
because different people came up with them, and
So they came up with the same, except the percentage of Hartree.
no, so the functional form is different in each one.
Okay, so actually exchange correlation part is different,
Yes.
not only the Hartree percentage.
Yes. And then, so with CAN-B3 Leap and Omega 97XD, they tend to be blue shifted because of the functional form of the exchange and correlation. I like to use both of these because I've found that they work relatively good, and from my experience, they're the most relevant. And if we go back to the list here, I went through all of these and got the papers, and for the iridium, the vast majority were PBE. And then there's some that,
PBE.
PBE0, yes. Then there was some that was PBE0 for the ground state, and then the excited state was in the Zora approximation, and then those were not as obvious what was going on because Javed and I have looked, mainly Javed, has looked at NWChem, which is the software that some of the authors use, and in that program they don't do 2DFT with Zora, so it's kind of confusing.
But there are also many publications should have not exactly PBE, but the tuned
Yes.
percentage of Hartree with moving from wherever it is, from 25 to around 38 or something.
Yeah, so depending on if it's red shifted or blue shifted, they can tune the Hadji-Fock. And typically when you tune the Hadji-Fock, the charge transfer states will migrate at a faster rate than the pi star. So sometimes, yeah, if you have, the absorption is, I'll just skip forward a bit. So here, this is comparing PBE0 to B3 Leap, and the experimental is here. Sometimes if this first peak is very broad, it is a lot of times a charge transfer peak, and there's some cases where we first see this very strong peak, but if we tune the percentage of Hadji-Fock, then we can split that peak into two, and then we can say, oh, this is clearly a charge transfer, this is a pi star, and then it can better match the experiment. So then, depending on what you want to use these for, if we are trying to screen, because from previous meetings back here, I think his plan is to do QSAR, kick out new molecules to test, have DFT, see if they're reasonable, and then pass them on to experiment. So unless they are a dinuclear iridium complex, I would say PBE or B3, PBE0, PBE0 or B3 Leap would be good to use as a screening functional. Possibly use both to have certain that they are similar. And I already showed you this slide. So these are the ones. This is not published yet, but it's in draft. So here we compared B3 Leap and PBE, as I said before, and really the major thing that changes is the position of the peaks between them. which
But this might be an issue, right? Because let's say if we're interested in getting the main goal for the whole kind of businesses for new project is to find in the materials which will have emitting properties at the infrared range, right?
yeah.
So we really want to shift the slow transitions with optical activity to the red. And now if one functional is artificially too much redshifted rather than another functional, right? And then how you know which is right? Like which is really goes to red and which doesn't?
So that is a very interesting question, and it's kind of one that I don't think has been like answered in the literature, because a lot of times when people look at these, they are dealing with experimental results, so they choose their functional to match the experimental the best, and they don't say, we have these class of materials, let's try PBE 0 and B3 LEAP and see which one matches best for 50 compounds. So that might be a thing that we need to look at to say, if we use B3 LEAP, we can normally expect a shift of 0.1 EV, or a shift for the other functional of 0.2 EV.
What about if you do like, rather than taking a small group of compounds after screening, if you take the broad group, like relatively longer, bigger group, and then run the calculation with the both functional BB and Chem.
No, this is what he says
that's
he's going to.
I didn't say
But
I
let's
was.
say you're taking 50 compounds, right? Suppose there would be 50 compounds with iridium, and for all 50 compounds we know already the spectra from experiment, right? And you run them both with PBE and with relief, right? Then you compare with experimental data, and let's say half of them goes good agreement with bis relief, 20% showing good agreement with bis relief, 80% going with PBE 0, right? And the rest is neither of them is really satisfying. Sure. It means that you need some modification.
Yeah.
Then the question is what to do in this case, like because, and it's actually the question back to you. Since you already.
Okay, what question?
I was also another problem is how big is your pool? I mean, from the project is like 100 is very big number,
So
or
Well,
50 is very
return
big?
back to your very first slide.
I think.
Yeah, can you kind of show?
If it's
Oh, whoops,
10
that's
I mean, not
One.
really.
One.
Oh, questions.
No, I meant one, but it skipped all the way back.
If it's just 10 or 20, you can.
No, I
from the
think from the
individual-
last presentation
Yeah.
we had with Dr. Soom.
This is a list of papers.
Okay.
This is 70. Technically, in each of the papers, there is like usually one paper goes to a series. Usually, it's
Yeah.
one serial, right? Series.
Series, yeah.
In
And
one paper,
each
one
series
series.
is usually there might be two series kind of combined together, but very rare. Like majority of them, just one series. Series means that it's
Yeah.
slight modification to the ligands. So kind of the class of ligands is exactly the same, but we put in just slightly modifying conjugation or some groups. So which goes from 3 to up to 10 in
Yeah.
depends, right? In average,
Per
let's say
paper.
5, right? So each of these paper has 5 guys with slightly modified ligands, which we can belong to the same series. Which means we already know that for this series, at least for this series, the same functional works. We have a very nice agreement, at least qualitatively or even quantitatively, with experiment inside the series, inside each paper.
Okay.
But now if I take 70, so it's actually 70 times 5, how many compounds you can calculate?
350.
So now we have 350 compounds, right? And you calculate it with bis relief and with 2 different functionals which are supposed to be working the best for either this or that. And then you really can clearly see that, yeah, this percentage works with bis relief, this percentage works with PB1, and some of them work with neither, means they're not really working. You need to do some tuning for the functions. Then what we are doing after that stage? How we can, because you expect us that we just give you one specific methodology for 350 compounds, right?
Right.
And then you will figure out what to do with that. But we have more.
You cannot
More
use
wo-
just one
Well,
No,
again,
we have
we
not.
can find the class. Let's say we can find that 100 of them definitely works with PBE1, for example. From 350, 100 of them works with PBE1 in a good agreement. And we, of course, can give you this 100. However, another 50 will work only with B3 leap. And PBE gives really too much spectra, show spectra. Sometimes it's not very big difference, sometimes it's more crucial difference.
So
these
are the ones, like this is a series. So what we did is, or what they did, the CN ligand, so these ones were not modified. The NN had pi conjugation here. So there's no phenyl ring here, now there's one and then
it's
two.
longest one. So
Yeah.
just conjugation is changed here.
So then if we take the experiment, which is this dash line, which I should have just had it solid. So this is an experiment, then these are the two functionals. So B3 leap is black and PBE0 is red.
So what is your conclusion for this specific series? Which is better?
So for this, the absorption it doesn't really matter. The thing that does somewhat matter more is the emission. So for PBE0, the emission's around 1700 nanometers, where when they took the far infrared emission, it's like the lowest is like 1,000. So we're rather largely off, but if we converted this to electron volts, then it would not probably
But
be
again,
as bad.
at least the trend is good.
Yes, the trend works good. So then if we go to B3 leap, and it kind of got cut off, I think this is 400 wavelength. So then this one shifts. And then we have good agreement. And Dr. Soon liked this one better, so in the paper we're going with B3 leap because it worked better.
Is it shifted only 400?
But at least you know
Yeah.
for what
But it's very small. and
material,
tiny.
Yes.
what function you can use, right?
Is it
For
the-
example, for iridium complexes, you know that the PB.
No. How many? Not all 70 papers were on iridium, right?
No.
This was only on iridium.
So there are iridium. So there's a lot on iridium, a lot on ruthenium,
Well, let's
and
say
a
we
few
have,
on platinum.
from these 70 papers, we have maybe half of them on iridium, for example, right? So you have, 30. 30 papers are on iridium. Again, we multiply 30 by around 5 in each,
150.
in average, right? So we get in 150. And then from this 150, some amount, maybe half, maybe 60%, whatever, right? Will work with this functional, another will work with other functional for absorption. And then for emission, it's even more complicated story.
Yeah, which we'll get to.
Okay, but at least can you find some kind of the systematic
No,
thing
there is
over
no
here?
systematic. Yep. No, this is exactly the problem.
So it's not
There is
connected
no
with the
systematic
metal,
way-
it's not connected with the ligand, it just randomly
Well, as I said, like, it's,
once works
it
with
might
these
connect,
systems.
it might connect with ligand, who knows, but it just, whatever the reason is, that from 150, 100 of them really has a very good trend with PB0, and for another 50, doesn't work with PB0, but works better with, I don't know, B3 leap or maybe even with other function.
Yeah. So there was one where
That's
we.
bad. If it's so random, let's say. If you would know that, for example, for the iridium complexes works this function for.
We kind of know it. We can put it if you put it in the probabilities, then of course we know that PB0 is more probably better choice for iridium, and if we go with ruthenium, it's not PB, right? It was
Ruthenium is
B3
B3 dependent.
and with ruthenium, B3 is better, right? So, but again, it's not it's a probability. Means you will always have some set of molecules which we calculated, which actually doesn't follow this trend. And there's no clear reason why, right? We really don't know why in this case PB works perfectly, and then we just slightly change the ligand, and somehow instead of PB we need to use something different.
So it might be if we looked at all of these papers and we converted them into XYZ and then ran them, we might be able to get some
But I guess
property. What?
when PB is working and when this is working.
But-
Maybe, depends on the geometry, right?
Or like, if you're functionalizing it with a electron withdrawing group or donating group, or if you're doing pi conjugation, like we might be able to come up with a, not like a rule book, but like we might be able to be like, oh, we think
It's
this
not.
is the case.
It should not depend on the conjugation anything, because again, this is exactly what we do in a series, right?
Yeah.
For series, we usually have the consistent
Within one
behavior,
small series.
which means you have same ligand except one written back to your guides. And here it's 3. Sometimes it's up to 10, right? Depends on the modification.
Mhm.
So here we really just kind of focus on one specific ligand, right, and just slightly modify this conjugated part, right? And for this one, we clearly see that, yeah, actually both functions not so bad,
Yeah.
and we have very clear trends. But if you go to a different series where the ligand might have completely, do you have any example of other series, no?
No,
But you can imagine that instead of whatever the names of these guys, you can put bipyridines, or you can put something else. And then, instead of PBE, it would be some different function. So it's really dictated by the ligands. But what exactly in
So
the
not
ligands?
by the metal.
And metal too. It's like, for example, for ruthenium, bis-Philippe is usually better. For iridium, PBE is usually better. But usually doesn't mean always. And in some cases, we see that bis-Philippe works
Can
okay.
can you try to check the several more functionals and find which
This
one
is we
can
have done.
you have done?
And said like, again, there would be some percentage working with this, some percentage working with this, and some percentage, some where you really have to be creative and try different. Like they really, no trends. You really kind of randomly found the function. Oh, this works for this function. This works for this function.
You know, I have this kind of idea. I mean, what I can do. If you will be able to find some function which works for this particular metal, and with any kind of ligands, but for this metal, and then another function which works, for example, for ruthenium well, then I can create the QSAR model where we will, as one of the variables, to put the what kind of functional used for this. And then this QSAR model can be tunable. I mean,
So it's like additional parameter. Which
additional
you can
parameter
involve
which
in
is
the
like
system.
functional, and
So-
then we can make
and
it
again,
universal.
It's probably not just depends, and again, it's another question. Does it really depends on the part of the GGA part, means like PBE versus bis-Philippe, right? Or it really depends on the percentage of hard reform, because typically what happens, we start with, let's say, PBE, we know PBE is working for iridium, so we start with PBE 0, and if it doesn't, and go to your spectra, and PBE was black, or what I can see?
PBE is red.
Red. So red looks not perfect, but probably not really very bad, right? But technically, we missing a little bit
Yeah,
of this
we
extra.
It
kind
just
of-
shifted, right?
Yes.
But
It's shifted, but we
the,
also
the
out of
trend is
this-
the same.
Kind of, yeah. The trend
Kind of the
comparing
distance
these three,
between
right.
the signals.
But we're also missing kind of a feature, this peaked
Yes.
thing.
So there, if I put the oscillator strength, there are peaks here. It's just
Not
the,
distinct.
these strong ones overshadow it.
Yeah.
And this peak is associated, I believe, with this like this ligand. So it's a interligand excitation.
But of course, you should really put two limiting cases. One case when you're showing that, yeah, you have very good agreement right away with whatever you're functional, right? But we can definitely find a very easy case when PBE will not work at all, and like it would be really significant shift. And then what we usually do, we not really and if you do bis-Philippe, it's very similar, not really any choice. Bis-Philippe might be too much blue shifted anyway. So then what we usually do, we stay with PBE, but we change in the Hartree-Fock portion. So it's not just coming from one function to another. We still can probably claim that PBE 0 is the best for iridium, but in some cases it's best with 25% of Hartree-Fock, in the other case it's best with 30%, in the other case it might be more, even larger than 30%.
Or less than 25.
Or less than 25, or something like something. But if it's less, it's usually bis-Philippe is better than, because bis-Philippe is 20.
But if you,
Well-
B3 leap has less than
bis-Philippe 20 and PBE 0.
yeah. So
25, sorry.
yeah.
So if you go less, then it probably means that bis-Philippe is better than
But
PBE. But anyway.
if you wanted to stay with one functional, you
Yeah,
can tune
so,
it that way.
so technically you probably need it's kind of two parameters. One is just being with the same functional and just tune in the Hartree Fock portion, which is, I think, very easy way to put it as a parameter in your model.
Yes, it's possible.
Or we really try different functionals, not
So-
just the Hartree Fock portion.
The best scenario will be if you will be able to find for each particular metal the best functional. It doesn't matter how much the Hartree Fock contribution you have. It's just some particular the set of parameters you have for that particular metal.
So
Not like several within one metal. Just one, you will be able to find one
But this is
particular.
impossible.
so
There's no one functional which will work just because it's a iridium metal organic complex. It depends on the ligands, unfortunately.
So why do you need to have the DFT functional incorporated into your?
You know, the main goal is to be able to predict the emission or absorption for that particular system,
Yes.
right?
Yes.
So based on your computations, I will build the QSAR model, which will be able to predict emission or absorption, exactly emission or absorption for the virtual compounds, which are not existent.
So you're going.
I just put the XYZ coordinates and it calculates for me the emission absorption
so
quickly,
you're
within a
going
second.
But
to
maybe we can put it in a different way.
predict the oscillator strength and the transition energy, or
Yes.
the shape of the curve.
No, first we need just the
Only
energy
the
of
strength,
the...
just one number.
So then, why couldn't you just put in the best functional for each compound?
Because the predictions will be...
You know,
Because
it would-
he trained his program for this number of sets, let's say 100 or how many we will give to him, right? And then he will do 1,000 new molecules,
Yes.
right?
Yes.
But then these 1,000 new molecules might be completely wrong. The results based on a bisphily functional for this new 1,000 molecules will be off. Not because the model doesn't work, the correlation doesn't work, but just because for this some of these compounds will be better to use PBE rather than bisphylline.
So
be more
could,
accurate. So in other words-
Originally, you have only one trend, function of an argument. And if you change function as you go, it is function of an argument.
So
Which
could
makes
you-
things complicated.
build two QSAR methods, one for PBE, one for B3 lead, and then
Yes.
compare the
yes, I
results?
can, but you're saying that there are more of them. You cannot focus only on PB,
Yes, but
E, and B3.
No, more, but
the
there's still
vast
counted
majority
number.
work for either PBE or B3 lead,
Or change in the Hartree Fock percentage.
or that, right? So if we used both functionals to do the calculations,
Can I do?
Before we go there,
Oh.
is it possible to do the preliminary step before predicting really the
What
properties, right?
kind of preliminary step?
I will tell you. Because we don't know. Again, what we know that by whatever reason, if you really go, like if you're in a Syria, usually we don't need to worry about functional. If we found the functional which works, right?
No,
Then
I'm just writing for
then the
my
trends
note.
and overall even quantitative behavior is also in a very good agreement inside the series, right?
Mhm.
However, if we now go from one ligand to another with the same metal, but really only modifying the ligand, completely going to a
Right.
different class of ligands, right? Then, oops, the functional is not working anymore. It should be a different functional. But we really never really put the question like why, if we go with this ligand to that ligand,
Right.
this functional is better than that. So maybe we can really first search the correlations and get some ideas that what exactly dictating in a structure of ligands mainly, it's not metals, it's really ligands. Why PBE working in one cases, but some other functional works in the other cases.
Right.
Or why PBE at 25% works,
Yes.
but then there is some amount where you really need to go to 30 or maybe even 35%.
So couldn't we use QSAR to
To answer this question, right?
out the functional percentage of Hartree Fock?
Yes. This is a question to you now. Can we do this intermediate step first to figure out what should be the structure of the compound and first say, oh, if you have this and this and this in your molecule, then use PBE and then you can kind of
Bin it.
make a class of metal organic complexes with these ligands and then whatever the small modification of these ligands, right? Which will always should be like the resultant will be trustable for PBE if you do calculations with PBE. And then you say, oh, but if ligands are this instead of that, and whatever small changes to that, then it should be the other functional.
So
Is it
pretty-
doable?
It's possible.
Pretty much do data
It's
mining
possible.
to
Oh, this
find
is how
a
you call it.
correlation between structure and which functional.
Yeah.
And then
It's
take
possible
that.
to train a model which will be able to predict this
And
kind of
then-
thing.
I think we need to do this first, and then after knowing this information, we really make different classes
Yeah.
on the same on the same metal, but with different ligands, right? And class working for this, class working for
So
that function.
characterization. And you say put it in this bin, or this bin, and then have
And
a
then you
feature
train them
method.
differently, and then you scan not all of them at the same kind of scanning procedure, but really break it into 3, 5 classes and scan them one by one.
No, yeah,
Oh,
it's
okay.
possible.
Scan them
It's possible.
separately. Is
It's
it more
possible.
complicated?
Yeah,
Or? This of course reduces the overall number of molecules which you can use for training. Because now instead of 150, you will have only 50 like this, 50 like that, and 50 like that.
right, because I wanted to make some universal model which will just put the XYZ coordinates and it will automatically
But
give
I,
us
But-
I think
now
this is
we are kind of
impossible.
splitting to small.
But I think this is impossible for the
Because I didn't
metal-organic
expect that
complexes.
for the same metal you have several functions which were good for the
And the reason is probably
its
because,
properties.
again, for low states, this is metal organic, this is charge transfer states which goes from the metal and the ligands, right? They hybridize.
Sorry.
But the level of hybridization, right, with the metal would be, of course, different if you change in the ligands. Of course, it also depends on the metal, but and the overall octahedral or whatever structure. But in some ligands, you might have more stronger contribution of this hybridization. In some cases, ligands might kind of prevent this, like make it less
So-
hybridized. It still will be charge
Ligands
transfer in
feel
nature,
strange.
but not with with some different features. And these features really very sensitive to the functional. And this actually probably explains why we have this difference with the functionals. Because this correlation is really sensitive to this charge transfer character. So I mean, we have a good explanation why it doesn't work. I mean, that's why I said like your model cannot be as simple. It probably has to be more complicated one. Nothing wrong to have more complicated model.
I thought yes,
Right?
it will be still complicated because we are gonna still add several functions, like one more variable which you're gonna say this kind of functional you have to use for this particular system. For example,
But this might be valuable scientific information
So
by itself. That kind of give a guidance to people who calculate, just saying, oh, if you have this and this structural parameters, then this is a choice of your functional. Right now, I think no one really knows
Right.
for 100% which functional to use based on the geometry. And if we can give this kind of guidance by itself without even going to infrared spectroscopy and so on, we can just write paper about this, and I think it would be I'm pretty sure the citation index of such paper would be very high.
Really?
Because everyone will be using it as a textbook, right?
as a benchmark.
Here is my, they will be just using it like, if you put it like a table or something, they will just check whatever the ligands are. Here is, the guru said this is a function which works. Then they try, and if we write, then they will cite us and
Yeah, so we
be
can
happy.
train a model which gonna based
How do you
on
do
your
this?
initial information predict what functional gonna be better for this particular ligand.
And I think maybe
Right.
this first step, what we probably need to do
Let's
right
do that.
now,
I mean, from
right?
my point of view, there is no
as initial
problem.
step, before going to really information about emission or how we can predict emission and so on.
So
So we can put it just absorption spectral calculations to make it simpler and just figure out what will be the function for absorption spectral calculation and what correlations with the structure. And then we can do as a second step for emission because they not always correlate as well. And emission usually very much. Right?
so this is what. Oh,
Okay, it's not visible, something.
The top is not. Are you supposed to see?
Yeah, this guy.
Ah,
there must be some light.
Yeah.
So what you're saying
it's reflection.
is take your XYZ coordinates from embedding through whatever smile string you have and then use like RDKit or OpenBabel. Take those, plug it into a classification which says B3 leap, PBE 0, B3 leap, PBE with 20%, 40%,
And maybe we can also use chemistry because
Sure.
sometimes we use chemistry.
whatever. This can go on. So once it goes in the classification, then you go into a prediction, which each one of these has its own model. to predict. And then from the prediction, you get oscillator strength, and excitation energy, emission, and
Right.
things like that.
Right.
Yeah.
So it's still one model. It just has
No, it's gonna be two models. One model gonna predict the
Functionals.
functional, and second model where we put that functional in the second model.
But the idea is that
The numbers from that function.
yes,
But
but
the idea is if you create a database, because this information will be just put it in a database. So after we generate this information, you don't need to do this step because you already know if this is a structure, then use this functional. You really don't need to do it through the
yes, but
through the methodology,
if
right?
we take chemical soup and we throw a iridium or whatever complex together, we still have to take the XYZ, classify it.
Oh,
then-
to be sure.
Yeah, because we don't know what it is, right? So then this way, yes, it's model on top of model.
Step one, step two.
But in the front end, like if I go to it and I go to the .com whatever, and I say, here's my smile string, it will say, oh, we think you should
will
do
give you the
PBE
final number.
0 and your first oscillator strings at 500
Yeah,
nanometers.
we can code it like put these two models in the code line, for example, write the Python code which will
Yeah.
calculate it. You just
So it means the user will not even know what's going on
not
inside.
even
Yeah.
know what's going on.
So they'll just get outputs and it will be oscillator strength energy and which functional is predicted to be best.
Right.
But I think it's, as I said, like, it might have really pretty significant scientific value by itself to answer the question. So what exactly making to be used, this function working better for absorption spectra, if you know the metal and if you know the ligands? What exactly dictates the use of this or that function?
And we might even be able to have like a probable. So we
No,
might
of
have
course,
like
it's probability.
five functionals and then one's 30%, one's 30%, and then the rest are.
Yeah, we're not, of course, getting that, oh, only this functional. We will still have some distribution in probabilities, but let's say we can make a conclusion that if you have the structural features, it's probably 90% of accuracy can be obtained with
By
this
this
specific
particular-
functional. Yeah, it's not absolutely correct answer, but at least you, how say, how it goes? Enhanced, right? Enhanced.
Certainty.
So, enhanced accuracy.
So,
or
but
something.
this initial information, at least you have to give it to me. I mean, this initial data. So for these
Right.
particular compounds,
But we need to figure
This
out
function
how
is
to
good.
how to organize, like what kind of organization should be
Would-
done first, right?
Wouldn't it just be? Right, that's one smile.
What is
it doesn't matter.
It's
Smile,
your
it's another representation, structure representation.
Ah,
Another kind of structure
so it's
representation.
like XYZ, but not XYZ.
It's yeah.
Okay.
So then this is what is the first thing, and then we need oscillator strength and energy, right?
Mhm.
Theory.
Why?
Oh,
Ah.
Whatever it is.
It's okay.
So theory, and then we also need with this experiment.
right.
So this part is really easy because we say E, right, from T to the FT, super simple. But getting how we relate experiment to this is more complicated, right?
So I will build a QSAR model which will connect this experiment with your theoretical numbers.
Sure.
And then answer the question. But we will create theoretical numbers, not just with a single functional. We need to really scan several.
Yes.
Right.
And one
And
of
then
the
your model will answer
so
which one
this,
is better.
The energy and oscillator strength gonna be like descriptors in a model, and one more descriptor gonna be there is what kind of functional. So they're gonna be like at least 3 descriptors.
I would say 4 because,
Functional,
because also the portion of
that
not
portion, okay, no problem.
But wouldn't the portion just be a new functional? So you have PBE 0, which is 25%, and then you
So
said
the new function, you just change the Hartree-Fock portion. That's it, right? You're not changing your GGA part.
sure.
So when you change in both the function, the GGA and the percentage of Hartree-Fock, you have more parameters to
But
change.
it makes a little bit complicated. If you somehow will be able to put these things together, like the portion of the Hartree-Fock and the function, like make it like one parameter.
Again,
That
same
would be
reason.
easier.
It's not. Because you might really have, even if the trends might be good, right? But they will be either too blue shifted or too red shifted.
No, I think are you trying to say you don't want two descriptors, one to say PBE and then one to say how much?
Because in that
percent?
case, right, because in that case I have to build this first model, classification, which needs to predict these two things. And I'm afraid this the second one of the portion of the Hartree-Fock,
Oh, but we don't need to scan.
it's
the
gonna
har-
be complicated
But
for the model to
we
predict.
not to go into scan the Hartree-Fock portion from 0 to 100, right? It's again, it's will
Yeah,
bring
so
us
if we
just
go by like fives.
a few steps. I mean, like it's, yeah.
5 discrete
Yeah. Numbers. Let's
numbers.
say, because we know already PBE starts with 30, so we go 30, 30, and we usually don't go more than 40. It's not good to go more than 40. So it probably goes with 25, 30, 35, 40. Or maybe 3 instead of 5, 4 instead of, you know, like, it's not going for all possible values in a very big range. It's really a few from pretty. Like in
Yeah,
other
I
words,
understand.
your window will be very narrow, right? Your window of, or the field of your parameters will be not really wide. And yeah, we can call it, let's say, PBE with this percent is your functional 1, PBE with that percent is your functional 2, and not really differentiate between, and then you have your bis relief with functional 5, and then Cambridge leap is your functional 6, right? But then I think it's not giving us completely the full picture, because it might be two things, actually three things which contribute. One, how is it important, the GGA part, because it's predicted differently based on the name of your functional. How is it important with your Hartree-Fock percentage, and how is it important to have this long range correction when it's kind of more scalar?
If we have a bin, like bins, right, and we say P20, P30, P40, B20, B30. So P is PBE, I didn't want to write it all out, and B is that, right? Then we'll have 10%, 20%, 5%, and so on, right? So we
Again,
would.
it doesn't answer you the question. If you want really to answer the question, what's the methodology to use, and what dictate in a molecule, what dictates this or this methodology, then of course just saying, oh, we have this percentage for this functional is not the whole story.
Yes,
Because it's, again,
you can say, oh, if PBE 0 or PBE as a functional has higher numbers as a whole than B3 lead, then that makes it clear that the functional form of the GGA function is important. Because
but your when they overlap, your bis relief 30 and your PBE 30, they have the same Hartree-Fock portion, but they have different GGA. So if you see there 20% and there 20%, then what does it mean? It means nothing. You cannot answer this question. Yeah. Only if you have clearly 100% with this will be, or
But
90%
I
will be
would
working.
postulate if you first characterized it as B3 lead or PBE, then the numbers for the type of functional I would assume would be similar. And in that case, you get so if
You're saying 50-50? What do you mean
or
similar?
similar. So the probability for functional A and functional B that changes the GGA functional, if they are similar in probability for working, or the output numbers similar, then I would assume that the Hartree-Fock portion would also be similar, unless the Hartree-Fock is super important. So if you have PBE and B3 leap, and let's say it's 50% chance that they work, right, with their given value, then you go to Hadrifak. It might be that 30% Hadrifak is the best. So then PBE
You
20.
even just you making your theory based on a specific assumption already. You already assume that you get the same result. You make your assumption based on this figure, right? Where you don't see a big difference between these two functions. If then it's not a question at all. If we have all complexes behaving this way, then we shouldn't even worry about the functionals. The problem is that we have I would say more than half will work like this, and some significant percentage will have a strong difference between these two functionals, right? You agree?
Yes.
And then, of course, the whole story would be completely different.
So if it's like this, where there's very low probability for PBE and the high probability for B3 leap to work, I would say that if you first characterized it as a GGA functional, that the model would say B3 leap is crap. B3 leap is good, PBE 0 is worthless. So I think that both ways will predict the same way. Instead of learning the physics
But what if not?
straightforwardly, you
But
can
what
back
to
it
do
out.
with those which don't work both for PBE and both for B3 leap? Again, you are assuming something. You're making a
But-
model based on some specific assumption, and your model has to be universal.
Yes.
Works for any case,
So
right?
if-
So return back and just try to remember how many times you probably it was not you, maybe it was mainly problem with Javed, right? There was several cases when we tried all possible functionals, neither is working. Yeah?
We also try to one
Yeah.
them on here.
And then, and again, we always have some such cases where neither of these functionals, which are typically work,
Yeah.
neither of them
So-
is working, right?
We can tack on here
And
more. I just was lazy to write.
and then again, the
100.
question is what to do with those ones. And again, I don't think that we have really 1 or 2% like this.
Yes.
We probably will have not half, but let's say you will have something around maybe 30% versus
Sure.
40 and 40, or whatever, 20 versus 40 and 40.
So you're thinking if you first characterize the base functional and then tack
I
on
put it
after.
differently. We should not limit ourselves to two
I'm
functionals,
not
right?
saying we should limit to 2. I'm saying if we look at B3 leap, omega B 97XD, or Minnesota functionals, long range corrected functionals, right? So if we have a slew of functionals, you'll say first characterize it based on the functional. Then for functionals that we modify the Hadrifak percentage.
Oh, you're saying like it's another step
Yes.
beneath it.
Is that what you're saying?
Well, yes.
So
Technically,
I guess-
we can put it this way.
I guess
So like you put it like algorithm, you're saying, okay, we have 5 functionals, so we check that these functionals, at least one of these functionals works. If not, if neither of them really good, then we can try again these 5, or we can choose those which works at least with some certainty better than the other, right? So kind of to reduce, let's say just 2, from 5 we choosing 2, which looks not so bad. And then, or at least trends are not so bad, right? And then you say, okay, go with changing the Hartree-Fock portion and find then which of these 2 will require 20 or 30 or whatever the percentage.
so. In your mind, why does determining the functional first and then going to Hadrifak percentage not give
Not
you
backward?
the same results as saying let's for PBE and B3 leap and any other ones that we can change the percentage of Hadrifak, run 5 calculations for each one, and then
Because you already doing extra steps,
But
right? Because you might not really need to worry about your Hartree-Fock if you already have, or you're not even, you can get your answer right away without really doing
But
the
in-
second step.
to generate the data set, we need to complete every calculation for each compound, correct? Or can we just, if we say, oh, this compound works best
For these initial sets, you probably have to do
But
that
for
to find the
initial-
best
For initial
functional.
sets, we already have the answer, right?
But-
Like this one, we
but
already know which functional is better for
We-
this
we
specific
can't-
case, right?
I would assume using QSAR, you would need to say, we have, for energy and oscillator strength, we have it for B3 leap with default hydrofoc with 20%, 30, 35, 40. So you need to calculate all of those. Then you need to go to your next functional. If that changes the percentage of hydrofoc, then you need to calculate those. So if we do PBE, B3 leap, and we do 5 different percentage of hydrofoc, then for those two functionals, we need to have 10 lists of energy and oscillator strength, correct? Or if we already know that this percentage works the best for
Maybe
this.
I didn't get it right, but initially it should be like that. To be able for me to train the model, I have to get from you chemical structure and exact functional and the percentage of the contributions, the Hartree-Fock and so on, so on, right? Structure, functional, and that's it. How you gonna find it? That's not my
Well,
problem.
you're saying
I
this
don't have to know about that.
this data coming based on the comparison of our DFT with experiment, and we given you this data based on the best matching, right?
Right, so you
But
have
then-
to check maybe,
but then- then in
5
your-
or 10 different
right,
combinations
and-
before you give it to me.
No, we suppose we checked it already, right?
Okay.
But you don't need to know this data.
I don't need to know that. I only need
Because
these final numbers.
Levi is saying that we need to provide all this data with trying all this to
You only have to provide me the
Those which
numbers
work
which
the
you
best.
need at the end to get from me to be able to know what functional and what the combination of these the functional contributions you need to calculate that particular structure.
So what you're saying, I guess I assumed that if we had functionals here and compounds here, if we look at the papers and we say, oh, this compound, we use this functional. This compound, we use this.
Right.
This, we use this.
Right.
That's all we need. We don't need to check every box.
It's up
For
to
you.
you. You
No,
check
no,
every box,
no,
but
I'm saying,
for me, you have to give only one.
okay.
to answer the question which function works for which geometry. Let's say if you're not asking the question what modification of molecule results on the most redshifted and the most brightest transition, if you're not answering this question, if you just want to figure out why these different geometries have to be calculated by different functionals, what exactly dictates the choice of the functional?
Mhm.
If you put this question in front, then you just need from us exactly the table which Levi, like
Right.
only those which are marked. You don't
Just-
need that each of these lines should have the data.
No, I just need only
The
one.
best.
The best.
Those which
and that's
works.
it. Yes, right.
Oh, interesting.
Yeah, that's. I guess I assumed that you needed this entire table filled out and then run your model.
It's easy for us.
Yeah, it's much easier.
Easier for you guys?
Yeah, because we have.
Because we have, like, of course, we're not doing this scaling, or how to say, scanning of functionals very, very rigorously. We just try a few, and if we see reasonable agreement and very good trends, we say, okay, then it's bisrelief as a choice.
It's for you, it's easy.
But-
But for me, for example, I consider these different functionals as different y's. Since, for example, descriptors, it's independent variable x's. And since I need to predict the function for you, I need only one y. I may have the different x's, so independent variables, but I only need one y. I cannot predict several y's or choose from several y's.
So you can't say, here's my structure. What is the probability of this working? So like in neural networks, if you have a picture and you're doing a convolution neural network and predicting if it's a person, a bus, a whatever, right? Then you give all the pixels, it runs through, and then at the output it has like person, bus, building, whatever, and each one of them has a percentage. So if the model is well trained and you put a person in front of it, it will be like 95% will be a person, and then the rest will be
A crap.
small. So that's not what you're saying. You're saying you give it a structure and it gives you one output.
Right, because since we are talking about classification model gives you one number. It doesn't
Not-
give you.
Not if you do neural network.
Well,
They give
we are
you
not
confident.
but we know.
Yes, yes.
We know that we don't.
They're,
Yes, yes.
they're
this
so-called
is a
binary
difference.
models where you have yes or no
Okay.
answer. Or they're regression models where you getting some particular number
Okay. So your
in some range.
yours will be, we give you the 550 compounds with one DFT functional,
Which works best for that particular
and then
compound.
you'll be able to get enough data from that. to
Right, that's
predict.
gonna be enough.
Okay. I figured you would need like mass data.
Mass data I will generate by myself. So per each structure, I will generate 5,000 my own descriptors. Which
So-
will be able to predict your functional based on that.
I guess then I see a slight problem because a lot of the times we say change it from 25 to 40 and then we say, oh, it moved too much. So I know in one of the papers I worked on, we did 37%.
So what's the problem? It would be just one of your functionals on this list then.
Yes.
You just call it PBE, not PBE 0, but PBE
PBE underscore
37.
37, sure.
Yeah, sounds like this.
So then is one data point significant in the model? Because I'm assuming from
But
what I
but
would-
Levi, again, the idea is that we probably start working with those which, like of course we always will have some set data which not really showing a good trends, right? Let's say for functionals, we always will have some guys which will have this 31%, and this would be maybe one structure, another structure which has some other functional working, but majority of them will be really on PBE, pure PBE, or maybe PBE 30, right? And then you can really choose to train your model based on those which are showing a very nice predicted trends,
I guess I don't think
rather
there's-
than go into this noise, to these deviations.
I don't think there's a ton of papers that have 30%. I think it has the percentage dictated by making it as close to experiment or quantitatively and qualitatively. So it might have 31, 32, 35, 34, right? So I guess I can look, but
I guess you have to.
I don't think that there's
I think we need to
significant
get this
number.
data first to be sure what we are talking about.
Yes, I
Is
don't-
it really that we will have all this 31, 32 spread over, or you really can see clearly that 90% goes just with pure PBE 0,
I think
and then
the
10%
vast
goes with some
majority
variations, right?
go with pure functionals.
So then maybe we can really focus on those which showing a very nice trend, and then those minority guys, right?
Sweep
We
under
can
the
address
rug
them
for now.
later, or we can figure them later, right?
Yes.
But at least we start with something we're showing a good trends.
Yeah,
Because
you can
cannot-
divide
if we
to
have-
these several groups.
Because let's say you have a group of 50 compounds showing that PBE is really working, and then you have a group of just 5 compounds. Bacteria is not able to get to work on these 5 compounds,
And that's
right?
why I assumed we would have to compute
But even
every
if you
functional and give it to him, and then his model would. Yes.
look, even if you take this, you have this only these compounds and calculate it with variations in Hartree Fock, but the output for this specific molecule that only 31% is working. So it means you still have only the answer because bacteria is not interested in whether it's 20% or 30% or 50. He needs just majority, right? It's either
Yes.
black or blue, black or white, right? So that's why even if you do all this search, it's not helping him
Sure.
to really
Then-
get his model work better. You still will have only 10 samples of molecules, not tens times tens due to the different functionals, right? This is, I think, the big difference. Like increasing data in different way how you calculate it, not really increasing the actual size of of actual
Features.
useful
parameters for
me.
him.
So then I can look like a quick glance,
And
but
if we
then
really
I would
have this
assume we wouldn't
noise,
need
we
to
just
look at
probably have to
Hartree
swap it
Fock and
out.
just say PBE PBE, B3 leap, maybe can be 3 leap.
And again, if you have 30, 31, 32, you probably can think that this is very close.
Sure.
This 1% is really nothing, right?
Sure.
And you can just call it 30s.
So then emission, solvent, we use the same solvent, but that doesn't really matter. The thing that might have some kink in the cog is Dr. Soon has a lot of different solvents. I think majority is dichloromethane and acetonitrile, and we use this.
We usually do a
GM.
solvent.
Is she need to predict what solvent she
No.
needs to use?
No.
They do different solvents to predict the nature of their transitions because pi-pi transitions versus MLCT behave differently.
Different
Like solvent affects more MLCT rather than pi-pi. And if they clearly see that there is no response, it means they know something about nature, that it's pi-pi, yeah.
And then they also look at solubility sometimes. So for the photo physics, they need I think a high concentration. So if it's weakly.
No, but I think this all information could be added through the experimental data. I don't think we
Yes.
need to worry it on a level of theory, right? Because you will have this data anyway from here, from experimental.
From papers, right?
Solubility, whatever, polarity of the
Right.
solvent and all this kind of stuff.
So then, how to predict emission? So Javed and I.
A second, before you go there, this is the most, emission. With emission, this is the most tricky and the most incorrect part, which we have the least predicted, or how to say, the least agreement.
Experience.
We have a good experience, but we have still not really very successful
Unclear how to
predictions
do.
on experimental data. The best thing which we can predict the trends, but even with the trends, the energy never really fits exact. Like absorption spectrum, we can
You
be
can
very, very
predict
good.
trend.
So like
I can make a QSAR model which can shift for that particular
But sometimes even
structure
trend is not
to
predictable.
the and make
Yeah.
it close to the real experimental.
So like in this case, some of them like the B3 leap is close, not B. PBE 0 is closer in energy, except for 3 that's way down, and then over there, there's 2 of them are shifted more red.
But in this case, it's not just not predicted. It's probably like having what exactly is the energy of this blue?
This
peak?
one, it's about 1700
It's
nanosecond.
pretty small energy.
1,700, and if you put it in some volts, like it's
It's
unrealistic
like a
value.
quarter, 3/4 of an electron volt.
About 0.7.
Like if you can talk about black and red that they just shifted with respect to experiment, right? The blue one is not just shifted; it's completely unrealistically going to the red, and of course it means that we were not able to really take the right.
But if it's always
State.
like that for all the compounds,
No, it's
Not
again
always.
some of them not so bad, some of them. Oh my
But-
God,
it's,
what's going
bad.
on there?
So it means you cannot even predict the trend. If
Yeah.
for
It
some of
is-
them it works, but for some of them it doesn't work.
So
You cannot
we
predict the trend.
still say that we can predict the trend for majority of them.
for
But-
context, these are charge transfer states. This is a pi-pi star. So if we look back at the structure, the blue one is only involving this guy. And from what I've found,
You mean for the emission?
yeah,
Emission is
the emission
from
is
this
only
state,
on here.
from this.
For this pi-pi star. And I have the emission in a bit. So when it's pi-pi star, I've always seen it shifted crazy down. When it's charge transfer, meaning it goes from this guy to here or this here, then it's not as bad. So now if we look at how to predict it, there's 3 classes, I would say. So analytical TDFT, we use the optimization of the excited state. So if we look at an animation, you excite with a photon, and then I zoomed in. So we're at where we were at the black, and then each step we do, we have to run a excited state calculation, so a T to the FT, and it depends on how far you are away, but then each one of these hops requires a T to the FT calculation, which is on the order of like an hour on several CPUs, which is highly time consuming. And what I did not put up here is Javed and I, when we use this, we have to consider different types of potential energy surfaces. So sometimes the first excited state gives us some good trends. Sometimes we have to go higher on the potential energy surface, which means we have to increase our computational cost to get the correct trends. So for a screening method, analog or T to the FT would be rather computationally prohibitive because it might take a day or so, or even more, maybe a week, to run analog or T to the FT on a organometallic complex on a full node, which is rather costly. So other cheaper methods, so pure delta SCF, the reason why I say pure is it just uses the FCF energy. So it takes the FCF energy, so you run a single point calculation at the ground state minima, then you optimize on the triplet first excited state, so you do a spin flip and then you run ground state DFT, and you get the excited state geometry, that's an approximation, and then you run from the triplet, the triplet state and the singlet configuration, and then what you can do is you can get limits. So if you go 0, 0, that should be the highest excitation, de-excitation energy, and if you do vertical, that should be the lowest. And hopefully that is like the lower and upper bound of like any Frank-Condon like progression. So we can get this energy, or it might be that some vibrational state here overlaps the best, so then you get vibronic like the pi star. And if we consider going from the vertical, because we have one geometry, so we have the same geometry here and here, we can think about doing a T to DFT.
So this is the easiest way, right?
Yeah, so this is the easiest way.
It's like within a couple of hours?
Yeah, so I would say, depending on the size of your organometallic complex,
Yeah, a couple hours probably is good.
it's probably...
If your ground state is there, if you already got your the geometry in the ground state calculation.
Oh, it's no time.
If it's optimized already.
Yeah, if you have the optimized...
No, you still need to get the triplet.
Yeah.
Optimization and then calculate
So you
the triplet.
optimize your ground state singlet and your triplet state, and then you run one FCF calculation. So no optimization, just a single point. So you have 3 energies, and then you take.
You still need to optimize your triplet state.
Yeah, so ground state and triplet state optimization, and then singlet ground state. So this is really cheap. What is almost at? The bottom one isn't shown here. So to get some understanding of the type of excitation, we did spin density, which you take the ground state singlet minus the excited state triplet, and you take the difference of the densities, and then you can see where the electron was and where the electron is going. So like here, the electron is on, it's hard to see because it's small, but this is on the CN ligand, and then it excites to the NN ligand. So this is also relatively cheap, because once you have the calculations, it's like done. This is really only that easy to do in vertical excitations because your geometries are identical. So if you do 0, 0, you have to figure out how to take the difference, because then the geometries change and it's a bit harder to do. So then if we look at T to the FT, if we go back here, T to the FT delta SCF just runs a T to the FT calculation from this geometry up. So it's, I would say it would take about 45 minutes longer per one, depending on your node. It scales on the size.
But with pure delta SCF, you're not getting vertical, you're getting only 0, 0, right?
No.
You can just take triplet geometry and calculate it in a singlet. I see.
So then we can do T to the T from the triplet equilibrium geometry, and then we can look at the NTOs, so transform from the eigenvalues of the ground state to a different basis, which has less molecular orbitals involved, and we can see the trends are similar. So either T to the FT delta SCF or pure delta SCF.
But just a second. When you talk about pure delta SCF, you're not what you show in ground state orbitals. You show in homoluma, or what you showing there?
So this
is
is taking the triplet density minus the singlet density
Okay,
at the same geometry.
I see.
So
So it's not even orbitals; it's just different
Density.
densities.
and this was a question of a reviewer on a paper. They're like,
Yeah. No one. I mean,
yes.
it's just information to me, but I got it.
So then if we compare vertical pure SCF methods versus T to the FT, the trends are about the same. 0, 0 is the highest in energy, and then vertical goes down, and then T to the FT also goes down because of.
But again, the main point here is that when you do with TDDFT from triplet, right, you really have an excited state.
Yes.
And with the pure delta SCF, you kind of in a ground state approximation,
Yes.
which again, not necessarily, like, they show some similarities, but maybe only for this complex. We're not having this information for all of them, right? That's why I wouldn't really say that, oh, either this or this should give you a good agreement. Depends again, we're not able to answer this question yet.
Even using delta SCF approaches, it depends on your structure. So I had one series that we had the energies correct, but the natures were wrong. And then I went through analytical T to the FT for like 2 weeks running a whole bunch of calculations. And then it turned out, if I start my initial conditions differently, I get the right trends.
Can you go back to your file with these parabolas to show you kind of picture? So, yeah, this one. So the problem is when we go with either of these methods, right? You kind of assuming, we don't know like the crossing between red and blue, right?
Mm-hmm.
Not necessarily, if you're assuming that there are dense states and there are more than one single triplet state, right? If there are somewhere another triplet state which can cross with the red one even earlier than the blue is crossing. And even this another triplet state is not as low as this triplet, right? As a T1. But if they cross earlier, it might end up with completely different triplet state and emit with a high energy rather than this one. So the problem is that neither of these approaches really secure that the state which you get after you kind of get in this low state, that this is really the right state where you really have an experiment. Because there is no any conditions or any, constraints kind of to really figure out. Again, we have many states which different in their lowest position, right? But if the crossing, but we don't know where exactly this crossing and
So
to
like
which state the
this.
crossing is happening.
So it might come on this state, and then it might go to an excited state here, and then emit.
Yeah.
Mm-hmm.
Because this low state will never be reachable, right? In this case.
You're right.
And that's why it doesn't matter whether it exists there or not, and whether it's optically active or not, you always will see the emission from T1 just because they have a stronger coupling probably or something which is not involved
a
in
higher
the
state. So I think, Javed,
higher state with low wavelengths.
yeah. Did you have a compound that the emissive state was T2 and not T1?
Yeah.
Yeah.
Or even not T2, T3,
But
T5.
eventually, but finally they found that it's kind of mixed with this fluorescence too. So
Okay.
they read on the calculations.
So, what I've used the most in mine, I've used T to the FT delta SCF. The reason for that is you can play with the initial condition to try and tune or almost manipulate your data. Like I didn't manipulate the data, I just manipulated my input, which then
But
leads
how you manipulate the data with delta SCF?
T to the FT. So I had
Oh, no, you mean you optimize TDDFT.
yeah. So when I optimize the structure, my initial condition.
Oh,
I
your initial
changed.
geometry is changed.
Yeah. So
You can start with different initial geometry.
and then that made it go to a different minima.
Potential.
Yes. So like depending on your starting geometry, you can get different results. And when I did that, the trends were incorrect. The energies were correct. The orbitals were wrong. But when I changed the initial geometry, the energies and orbitals were correct.
Yeah, you're doing pretty much the same thing. You will be explaining TD-DFT optimization of the excited state, or you're not.
That's
really.
this one. I didn't go into the math.
But it's all delta SCF, delta SCF.
No, this is analytical TD-DFT.
Oh, the very first one. Okay,
The
I
first
thought it
one
should
was.
be the last one. Okay, for analytical TD-DFT, we kind of doing the same idea of modifying the initial geometry, but in this case, you kind of say, take my you have your ground state and you have your TD-DFT, regular TD-DFT calculation of excited state S1, S2, or triplet, whatever you can have actually, whatever you choose. And then we say, choose state number triplet, the first triplet state, with the geometry as it was in a ground state, right? And do the optimization of the excited state. And let's say we got in very wrong trends. Then we say, okay, instead of first triplet, take the second triplet as initial and optimize the second one.
Well, how you can estimate you getting the wrong trend?
Or
We
comparing with
experiment.
experiment.
With experiment.
Only experiment, nothing else can be used.
So like if you forget that there's red and blue here, if we pretend that red is T2 and blue is T1, right? If we optimize the geometries, the nuclear coordinates are different, and the energy will also be different. So it might be that if we look at T2, the potential energy surface is not the minimum, but then if we take the energy from here down, that can correlate to the correct excitation, emission energy. Is that?
So we're looking on the trends and we're looking on the actual energy, like because if it's, sometimes we even have negative values. When we do analytical TD-DFT, it might be like minus some value, which means you're definitely choosing the wrong orbital kind of to optimize.
Right.
Yes.
And this is make all, and of course you always say, how you know that it's T2, not T3,
Right.
not T5? We
Right.
don't know.
You
And
don't
this
know.
is looks like we are cheating, yes.
So
In
there's,
between us, we always say we are
Can
again
we
cheating.
also? Can you also give me some initial data? Like for this particular structure, we used these parameters to get these numbers.
So this information definitely can give you, but again,
So I
for
could
most
also
cases,
give you some predictions. So guys, use this, take a
This
T1
would be-
or T2 or
this would be
this
useful,
one.
except that with excitations, how say, because because we really sometimes very often we really kind of just guessing them rather than really getting some clear idea. And also when we have a spectra, we always can check not only the lowest transitions, right? We look on the entire thing, and let's say if 3 peaks coincide, then of course it's much better than if I have a very good agreement with the first peak, but the other 2 will be off. Here with emission, we really can compare only the low state because we really get in just the energy. We cannot really look on the entire shape.
it might be at a later.
No, but my point is that's
your
why
head.
we even have no very good solid idea that what we got is really is comparable with
Yes,
expect.
but
The
if-
best way to compare
If
with
we
expect.
have spin over coupling, it might be that
It might be different, yes, because then you will have a line width which you can
Which-
compare with experimental data.
that's the last part of the presentation.
Oh, we're still not far away. I mean, I thought we'd done with this slide, no?
Yeah. So then different other ones. This is super fast. So there are some people that use semi-empirical methods to predict the geometry and excitation energy.
Okay.
So the first one, they're from the same people because it's the same research group, and yeah. So the first one, they just reparameterize the method and then plug that in, and you can't see it because I never remember that this is here, but the mean absolute error, I believe, goes down. So they say, oh, it's better, their method, and then from here you can run DFT to get the optimized geometry, or you can just say, I'm keeping this and I'm going on and running excitation or excited state calculations. So
So in other words, you use semi-empirics for geometry optimization, either triplet or singlet, by the way, but they check it only
To
for
get some
singlet.
initial
they only did some-
minimal structure.
Just to get the
Minimal
ground
energy
structure, yeah. And that, but it's hugely, it's like orders of magnitude difference
Yeah.
in calculation time,
Of
right?
course,
Yes.
So it's much faster. So you're really saving a huge amount of time. So we can, with this technique, we can really recalculate all these
Right.
things which were already calculated in 70 papers very quickly.
But can you try to use completely for everything the semi-empirical calculation, or it's
So-
not going to give anything?
What?
Was it parameterized for ruthenium, by the way?
Or
This
not?
is ruthenium.
So first of all, this is parameterized for ruthenium. Ruthenium means if you move to platinum onto iridium.
We have
But usually they created the PM6 and PM7 like universal ones for
Yes.
all
Usually, but not for
possible-
But-
transition metals. It
Not
never
for
works for
transition.
transition metal. No,
So,
nothing,
They
nothing
give a
universal.
list for what the
But here, even
metals it was.
DFT is not like even DFT, which is supposed to be universal, not universal for transition
So,
metals.
like,
Semi-empirics cannot be
I,
universal.
from reading this, the reason why they do this is I have taken from it that in the initial data set that they trained it on and did everything on, organometallic complexes were underrepresented. So they're taking the original one and they're putting the emphasis on organometallic complexes. And for this, I don't remember what all of these are, but they have a wide variety because they're looking at like solar cell applications, so they have like wide variety. So we could redo this for the 3 metals that we're interested in with the specific types that we want to look at, and then we can say, oh, we have very wide representation of the organometallic complexes, so we are confident that this should work for everything. But that needs to be done, and I have codes that can optimize them. It's just I've stopped because this same group recently published another paper on using CIS. CI, so now they're doing excitation. So they went from the ground state now to excitation, and they have MOPAC, it's a computational software, and they modified it slightly, and I'm gonna skip why, but then they can get the oscillator strengths and energies to some degree of they can have some,
Accurate.
what?
To some degree of accuracy.
Yes. So that might be a way, but that would take some time
I would say
to do it.
to use semi-empirics for geometry optimization is probably doable.
It's okay.
Oh, looks like we probably need some work and recheck that. Yeah, if you parameterize it for iridium or something, like slightly tune the parameters to be sure that we have a nice agreement.
So for ground state
It looks like
geometry
it's a
optimization,
way how
it's
we
gonna
can
be
go.
okay.
Yeah,
Okay.
although we not check for triplets, right? For triplets might be a different story.
So probably for
So-
excited state it's not good.
But for excited state, I would say it's probably too early. I don't think that it can be just taken and run it. So for excited state, we probably still need to do TDDFT.
So
Yeah, right.
I think if we worked on, if there was someone that worked on it, they could get it implemented to have some pre-screening to DFT. But I would,
But for again, it depends on the metal, depends on the molecule.
yeah, so if we did it for the metal that we're most interested in, and then we use the same methodology for the other metals, then it would,
It will not
But-
work. Yeah.
okay.
And it's not. And then the reparameterize it might take much more time rather than what you do for geometry. In the case of geometry.
Yes. And the thing with singlet triplet, they only thought about singlet, so what you can do is have an additional thing in your cost function that is dependent on singlet excitation and singlet ground state and triplet ground state, so your cost function gets more complicated. But that can be thought about later. So then if we look at spin-orbit coupling, at NERSC, they have QChem that we can use, and they do TDDFT with spin-orbit coupling. So what we are really interested in is the coupling matrix, because if we have these coupling matrix elements, then we can get a whole bunch of information that we are highly interested in. So here we can think about the radiative relaxation rates, So we take, what this is pretty much doing is perturbation theory, where you are kind of taking the oscillator strength from various singlet excitation, de-excitations, and seeing how much that couples the triplet, and then whatever that proportion is, you do a linear combination, and then you find the rate.
And I just so mu is dipole moment, or what is the rate of dipole moment? Transition dipole moment.
Transition dipole. So then we can get the transition for each component of the triplet state. Then we can get the correction to the energy for each one because of zero field splitting, and then we can get the observed rate down, and then we can convert that into lifetime.
And what it looks like we have different Ks there, right?
So, yeah. So if we look here, this is K for the first portion. So like MS0, MS-1, +1.
Huh?
Is it components of triplet?
Yeah.
So it's resolved for projections of triplet.
Oh, it's a projection of angular momentum.
Yeah. So MS -1, 0. And
MS means it's a quantum number.
So
Okay.
did you try to practice this? You can.
yeah. So I have it.
So what are the limitations or your experience about the productivity of it?
But just again, you already applied to metal organic complexes.
I haven't coded all of this in yet because
No, just to calculate spin orbit with.
Yeah.
Just to not
MS.
this course, but running the QChem for metal organic complexes.
Including spin orbit, right?
so it's
What's yeah?
I would say compared to Gaussian, off the record,
Yeah.
I don't want to get kicked out of Gaussian. The time is about the same. It might be a little bit longer in QChem for optimization. And then for
Optimization, geometry optimization.
yes.
Oh, but another thing, but you're not including spin orbit when you do geometry optimization.
Correct. It's just.
So again, you can use geometries obtained already in whatever method, I semi-empirics or or
Yeah.
Gaussian, right? And then
So
you just use the
if we
excited-
compare PBE0 with Gaussian's version of PBE0, it's maybe a little bit
About the same.
slower. But I found that T to the FT is a little bit quicker in QChem.
Right.
And that even includes the spin orbit coupling. I need to go in more and figure out, because there's the Tom Donkoff approximation, and then you have like random phase approximation. So depending on how all of those little parameters change, it might change a bit, but I found that it's about the same. The thing I found the most annoying is there's not as much documentation, so it's a lot of like trial and error before we can do it now. But now we have all of the stuff. Yeah, so we have the excited state to excited state, so singlet to triplet, that entire matrix. We have the XYZ component of the transition dipole moment. We have, this is the same one. We have these guys. Yeah, so there's 3 different couplings: ground to excited, triplet, then singlet excited to triplet excited, and then triplet excited to triplet excited. So yeah. And then we can just plug and chug and find what it is. If we look at the oscillator strength, this stuff virtually stays the same. So this whole term was in the previous one, and it was squared. So we can get the transition dipole, then we can get the corrected energy, and then we can get the oscillator strength by taking the complex conjugate, and then we can get oscillator strength. So bonus slides, I added this right before. So this is kind of like throwing the kitchen sink at organic metallic complexes because once we kind of know which functionals we can use, the only thing that really changes are the ligands, right? So if we have CN, CN, and N, typically these stay the same because that's how they make it an experiment, or it's experimentally
But
dictated.
there was also CC, I guess, right? Like when you have both carbons.
I think so. I think that's harder to do, but if you know the method to do it, then you can do it. So this is like very modular. So if you if you have a new ligand, you can put a ligand here and here, and you can change the function, the form of that. So it's like Legos. You can just plug and chug and do a
That's the idea, yeah.
combinatorial research. So this is another one that I looked at. This is another publication. So here, this row, we extended the pi conjugation here, and then here we left the CN the same, and we extended this pi conjugation again. And the reason why I have this is what the conjugation does is it lines where each one of these states are. So if you went purely by saying, let's take two ligands and see where the energies are, you might be able to come up with a way to say, let's independently throw CN ligands on an NN ligand depending on the energy difference in the homo-lumo, and then that might be able to be used to have low energy emission.
But again, when you say CN or NN or even CC, of course, various CN or NN ligands are available.
Mm-hmm.
So it's a class. It's not just
Okay.
one specific ligand.
So like here, when I was frantically searching at like 2:30, I was like heterostructure, substitution. So like we can change it to a whole bunch. So the chemical space is massive for what we can do, which is why QSO is so important because DFT.
Yeah, you
Takes
cannot
time.
go through
Right.
this huge number of
possible
compounds.
combinations.
Right, with the computational chemistry, right.
Are we far away from it?
I think
Because
this is
Dr. used to
about
run it.
question,
Ah.
but yes.
So the question is now, when you will be able to provide me this set of data we were talking about, like structures and methods you use, so I can train the model to
The
be able
initial
to help
idea
you.
was that we wait in the database, but you so now what kind of form, what, because again, the problem is how to organize this data, in what
you
format,
said you
in
have
what
some
way.
already experience, you calculated some of the compounds. Can you
Yeah.
give at least what you calculate, what you was
In
dealing
which
with?
format?
So
XYZ coordinates and just
So-
make one table in Word. That's the structure, number of structure. That's the functional you use, and then in a separate zip file, provide all the XYZ coordinates. That's it. Number it. I don't need anything else. At the beginning.
Or you can create this kind of table which you draw in, right? Like name of a compounds, and if we need to
So,
name them in a
have
way
you
how.
used like an H5 file system in Python?
H5 file system.
So, how about like NumPy arrays that are multidimensional? So could we give you like a NumPy array that has like R?
You can create a data frame by
Yeah, you
clicking
can do
down,
that.
and then you can read the data.
Oh,
Yeah,
what?
you can do array where
You can
which
use a
has
data
the coordinates and the functional use, of course.
Right, so then for like the first element, we have X, Y, Z, and then,
So you're just interested in our data, not
To
experimental.
help you, first of all, and then all these experimental data and your energy values that you calculated for these structures, right?
That's like
That's
what he's
second
doing,
set
right?
of data. That's, yes, the energy and oscillator values.
Right. And so if this is a
That's a full
Yeah, so
set
it's
of
a-
data. That would be ideal.
But the question is what format, right? Because you saying
format.
you can
He wants to give in
this format.
in physical format. I mean, like you send it as one
Mm.
file or what?
No, you have one file
If you wanna
For each
create-
molecule, right?
No,
no, he wanna
You
Because
have-
then
create,
coordinates
you
he wanna
have
create
a
matrix
position,
and send me this
functional,
matrix.
energy, oscillator strength.
for
And
each molecule.
No,
For all of them.
for the
So
entire
in
data.
one matrix, all the molecules data, everything.
So the first element corresponds to the first element in each one, and like for the coordinate, you have x, y, z of all of the atoms.
But for energies, you calculate absorption spectra, and it's hundreds of states, right? Up
Yeah.
to hundreds of states.
Doesn't matter. You just
They can put as many as possible to that matrix.
and if we need, we can zero pad.
So this will work.
I can
Okay, we can send at least
process
with
any
something
kind
and
of
then
data.
see.
I just need some data.
Okay,
I
so
can
we need to
process
create
anything.
this kind of like. Suppose let's go with this style, and we create it as much as we can. Right, means whatever the values are available so far, and then send to you, and then you will tell, and then we can kind of adjust it on
We
the
can-
fly.
yes, we can,
something
Do you have an account on Photon?
on CCast.
No, I'm assuming he has one on CCAS, but it's probably
But,
Fortran?
Photon, it's our. No, we never open user account on the
Okay.
Photon.
And for
You
No,
can
I
use-
don't. You mean
Do you
is
want-
the condo?
no.
We have
Your
local
own
computers,
class.
Yeah.
Not the
No,
class,
no,
the,
I don't.
So then,
server, but we
I'll-
can
Yeah,
of
your
course
own
make
server.
it.
I'll have to talk to you to give.
But what is better? We can put it. Let's say we can open account on our server, and he can put all this data on the server, and then you just take them from it, or your students can take it. Doesn't matter. Or you tell us where to put it on or we can put it
No,
on
no.
somewhere on the
You'll
CCast.
probably have to take it from my directory.
Right. You can put it on. You create a directory, let's say full Bhakti or something, or whatever the name, and then you tell him where he can take this, and this from CCast. I mean, from the Sanda account, Sanda how it goes, Sanda.
Because I don't think
What is easy way?
it would be good to email. It might be.
No. You cannot send it by email.
You
It's
can,
too
you
much
can
data.
create a one group directory for
depends.
this project and put everything on that
It
directory.
depends if it's just text
Everyone should have
matrix.
access to that one.
Yeah.
No, we can. The question is, just do it on a CCast? Or
Yeah,
we can do it on
whatever
our server, or
Okay.
maybe you have your own server.
No, I
You
don't
You can
have
create
yet.
an user
So
or
when
group or
when Javed and I or whoever does it, we can send you an email and say, what do you want us to do?
Okay.
Or you can just really put it on, create a directory on a CCast, I mean not CCast, how it goes, on Sanda, right?
Yes.
And with kind of for the group or whatever, for the project, and then we can ask just permission. If I think they changed this policy now, everyone or whatever.
It's not. It will change,
It's not
but it
changed
has
yet?
not changed yet.
But we can really ask for. Please make this directory be open to the group of Bhakti or and the group
So
of.
we might be able to ask for a project directory.
Oh, something like this.
Right. For some separate project.
So we can just make a request to CCAS,
possible.
create, and then we have this kind of project account or project whatever directory where where your information can be put there. Anyone can put, and then you just send email saying, okay, we put this data. Please check and tell me whether you like it or not, or what kind of things has to be changed.
Because you know how to use
They
NumPy,
need to
right?
create a new
I
group
know.
and then
Okay.
both of you need to put the same group.
Huh?
They cannot give access to two different groups. They need to create a new
No,
group,
no, it's
put
clear,
everyone
right.
in that group.
Sure.
and then
Whatever they do is what they do.
It's a technical issues, yeah.
Okay.
We just address like we send email explaining what we need, and whatever the ways they can do it, it's up to them.
And for this file, since the dimension of R and all other parameters are not same, it would be better if you create the two files, one for the R and all other in the one file.
Yeah, each one of these is a file. So I'll send him 4 files: position, functional, oscillator strength, and energy. And each one of those will have.
First line, for
Yes.
one compound, whatever's the name for this
Yeah,
compound.
if there is
Yeah,
no
second
number,
basically you can
you
put it on
can
one
just put
particular.
0.
Yeah, so you can zero
yeah.
pad it.
If something is missing,
Okay.
it's zero.
Okay then, great.
Ты говорил с Андреем?
Да, я послал email.
В пятницу.
So I think there's no questions. We're done?
No, we are preparing for
Где
living.
книга?
No.
Вторник, среду.
Вторник не будет запись.
Okay, let's.
В среду на два часа. Ну вот,
Где-то в
можем
среду
в среду
какой-то.
утром тогда.
So no questions.
No questions about
No,
which
you're
work
right.
meeting that.
Oh,
30
normally we're
времени.
clapped when we get here and then after.
Oh, you want another one more?
No, I'm good.
Можно встретиться где-нибудь там вот в этой в кафешке.
Да,
Wow, this mouse is really
weird. Потому что я не
В
знаю, он не
среду.
хочет.
А, он
И
хочет?
мне будет опасно, потому что я уже в субботу уезжаю.
А, ты же слышишь? Все, да, Миша?
Я вчера... Да.
Поздравляю. Все уже решено.